right, stoichiometry. Stoichiometry is when we are predicting amounts. Maybe we know how much of one of the reactants we have and we wonder how much product we can make. Or we know how much product we've got to have and we wonder how much reactant it's going to take to get it. So either way, we know one amount and we're going to calculate another amount. Now, the secret to stoichiometry is the map. This is a little thing that my classes and I have been working on over the past 34 years. And every time we run into a stoichiometry problem that we can't solve with the map, we add a piece onto it. And you can see it's become fairly extensive now. So I'm going to give you your very own personal copy of the map. And it's been a while since we've added anything to it. I think we may have it about as complete as we're going to be able to get it. Let me show you how to use the map. So let's do an example. All right, I need to make 36 grams of sodium carbonate in the lab, and I wonder how much carbonic acid I'm going to need in order to do that. First thing I need, the very first thing I need is the balanced chemical equation. All right, I know that my product needs to be sodium carbonate. And I know that one reactant is going to be carbonic acid. But the problem doesn't tell us anything else. That's all we know. And so this gives us a certain amount of freedom. We are free to pick whatever it's going to take to do this. We could choose to do this as a single replacement reaction and make our other reactant sodium so that we'd have an element and a compound. We could choose to make this a double replacement reaction and make it sodium hydroxide. We could choose to do all kinds of things. Let's do it as a double replacement reaction. So we're going to decide that our other reactant needs to be sodium. We need the sodium and hydroxide. All right, that means that our other product is going to be hydrogen hydroxide, also known as water. Now, is it balanced? Excuse me, cat. Well, we have one sodium, two sodiums. I'm going to have to increase the sides that's too small. Two hydroxides, one hydroxide. Two hydrogens that are not hydroxide, two hydrogens that are not hydroxide, one carbonate, one carbonate. Now we're balanced. Okay, we have a balanced chemical equation that will give us the products that we need. All right, now I'm going to label the amounts that I know, and that's pretty slim pickings. I know I need 36 grams of sodium carbonate. So under sodium carbonate, I'm going to write 36 grams. And I know I need to know how much carbonic acid I need. And it doesn't tell me what units I ought to use. It doesn't tell me whether I need grams of carbonic acid or milliliters of carbonic acid. So there again, if the question doesn't specify, it's my choice. All right, I'm going to say, just for the sake of keeping things easy on this first example, that I need grams. I need mass. All right, the substance that I know, I'm going to call A, just because it's a lot faster to write A than it is to write sodium carbonate. And the one that I want to know, I'm going to call B. Now, once I've gotten to this point, I've changed a word problem into just this very sketchy mathematical statement. And that just, it makes these complicated, intricate stories into something that's very cut and dried. All right, so I look on the map. I'm going to start with a mass of A and end with a mass of B. And so the map tells me I'm going to need 1, 2, 3 unit multipliers to do that. And if you've got good eyes, this probably doesn't show on the video. But if you've got good eyes, it will tell you exactly what each unit multiplier needs to be. Good stuff. All right, so let's start with what we know. We know that we have 36 grams of substance A. The first unit multiplier is going to get us out of grams of A and put us into moles of A. And in order to do that, I need the molar mass. So I'm going to come over here to the side and do a quick calculation of the molar mass. Sodium is 23, but I've got 2 of them, so that's 46. Carbon is 12. Oxygen is 16, but I've got 3 of them, so that's 48. And when I add that up, that's 10, 16, 4, 8, 9, 10. 106 grams is going to be the same thing as 1 mole. Now that gets us out of grams of A. That's canceled. Now I'm in moles of A. So if you look back at the map, now I'm here. I've gone from here to here. Now I need to go from moles of A to moles of B. And in order to do that, I need the coefficients from the balanced chemical equation. That's the only way to get from A to B. All right, looking at the equation, I can see that it's going to take 1 mole of B for every 1 mole of A. Well, that's easy enough. 1 mole of B for every 1 mole of A. And that cancels out our moles of A. So now I'm here at moles of B on the map. I've only got one more step to go. I need to go to mass of B. So I want to get out of moles of B and into grams of B. That means I need the molar mass of B. Well, we come over and do another little side calculation. Hydrogen is 1, but there's 2 of them, so that's going to be 2. Carbon is still 12. Oxygen is still 16, but there's 3 of them, so that's 48. 48, 58, 60, 62 grams to the mole. So 62 grams is the same thing as 1 mole. That cancels out our moles of B, and our answer will come out into grams of B. So now we let our fingers do the walking on the calculator. Okay, so now it's just a matter of punching buttons. I've got 36 divided by 106, no point multiplying by 1, times 62. All right, the calculator says this unrighteously long repeating decimal, but I've only got 3 sig figs, so I'm going to report that as 21.1 grams of carbonic acid. And there's my answer. Pretty painless, yes? All right, now that was probably the most common kind of stoichiometry problem, but by no means the only kind of stoichiometry problem. We could start with a mixture and work our way back around to mass, or we could start with the volume of a gas and work our way around to the volume of a solution. We can start at any of the green rectangles and work our way to any other green rectangle. The only thing you have to think about is that not all of these are unit multipliers. This equation right here, PV equals nRT, is an equation that you have to solve. It will not be done by dimensional analysis, and here it is going the other way. Just notice that all of the quantities that you know are in the top half of the map. All the quantities that you want to know are mirror imaged here in the bottom half of the map, but the only way to cross from the top to the bottom is to go through the balanced chemical equation. All right, there are lots of ways that we could do this, but we'll wait until we need to do it.